Well, hello and welcome everyone to the Integrate Professional Development webinar series. The Integrate project aims to promote faculty teaching about the Earth in the context of society. Integrate is an NSF-funded STEM talent expansion project. Its two overarching goals are first, to develop materials and curricula that are adoptable and adaptable for faculty to increase Earth literacy for all undergraduates. And second, to increase majors in the geosciences and related fields to develop a workforce capable of tackling environmental and resource challenges. This webinar is part of a series supporting teaching with Integrate principles, using the piloted and peer-reviewed Integrate developed and curated materials as tools. On the screen and in the chat box, there is a link to the webinar event page where you can find our presentation slides, resources related to today's presentation, and afterwards a recording of today's webinar. If you have questions along the way, you can type them into the chat box. To access that, find the Zoom control bar and click on the chat button. We ask that you leave your mics muted and video off. That'll help us get a good recording of the webinar and enter all your questions into the chat box along the way. So I'm happy to introduce today's speakers, Mike Coachella from Virginia Tech and Dave Moak at Montana State University, who present an overview of nanoscience and teaching nanoscience in your courses. The webinar will summarize the key concepts about nanoscience in the Earth system, recently published in a review article in Science, and also provide an overview of a new website that supports teaching about nanoscience in coursework with suggestions on what, why, and how to teach nanoscience. And with that very quick introduction, I'm going to turn it over to Mike.
Okay, thanks very much, Mitchell. Appreciate it. I'm going to, before I actually share my screen and show you my first slide, I'd just like to say that nanoscience is a relatively new science as sciences go. It has done a very poor job at being introduced into geoscience curricula. That's not the case in chemistry, physics, biology, and even the social sciences. So we're lagging, and that's one reason we're having this webinar. We're really glad that people who are online could join us today, and Dave and I are really anxious to talk about this as we have done for years. But we need to bring this more to the undergraduate level, and this was the dream of Dave Moak a while ago, and it's starting to work. At Virginia Tech, we do have an undergraduate major in nanoscience. In that major, two of the sciences are Earth-related. The others are bio, physics, chem, and so on and so forth. But that's very rare. We're the only program in the country, actually, that has an undergraduate degree in nanoscience. But again, today is just to help get it more ensconced into the undergraduate geo curriculum. Hopefully, Dave and I will convince you today that it is a necessary science. This is not a sideline science, and we're doing our best to get it introduced even to freshmen in the earth sciences. Okay, I'm going to go ahead to my slides, and I'll bring that up in a sec here. All right, and Mitchell, you can see that all right?
Looks good.
Okay, so I'd like to start with introducing at the top there, funded by the National Science Foundation, something called the National Nanotechnology Coordinated Infrastructure. And this is as you see down in the lower left, is in this 5-year period, an $81 million investment by NSF at 16 national sites. And two of the sites are Virginia Tech that you see in the mid-Atlantic states on the right, and up in the Pacific Northwest, Montana State University, where Dave is. And we are the two sites that represent earth sciences in this network. All the other centers mainly highlight nanoelectronics and physics, chemistry, biology, and so on and so forth. The site at Virginia Tech is totally dedicated to the earth environmental sciences. So if you look down in the lower right, our name is Nano-Earth. Dave can talk a bit about his center, but in ours, if you want to get a hold of us, just go to nanoearth.org, and you can look at what we have to offer and come and work with us, or we can come to you to work with you. in effect by doing samples that you're interested in having nano characterization done or nano properties done or whatever your nano application may be. And so literally Dave's site at Montana State and ours at Virginia Tech are open for business. We service people all over the country. We have many, many dozens of clients every year. We are in year 4, I guess, and we'll have year 5, and then we'll hopefully be renewed for another 5 years to go through the year 2025. Okay, in the Earth system, and a lot of us like to talk about the Earth system now, you have obviously everything everybody knows on this call: the atmosphere, the hydrosphere, the solid Earth, soils, rivers and lakes, oceans, you name it, it's all in the Earth system. And the Earth system was fitting together like a beautiful puzzle, but there was a big hole in the puzzle, and that hole was the Earth's nanomaterials. In the last 20 years, it's come into vogue. Earth scientists are thinking about this now and talking about it. And when you go to major conferences in the earth sciences, you'll see a lot of nano sessions and a lot of nano talks. So we're sort of plugging that piece into the Earth system. And let me put it in another context for you in this next slide. These are the major technological revolutions in human history, just actually 4 of them that started in the 20th century. So if you look in the bottom scale there, the 1930s, and that top purple bar is when the molecular biology revolution started in the 1930s. The cognitive sciences started in the early 1950s. The nanosciences, the third arrow down there, as you can see, started around 1960. And the digital and information revolution started in the late 1960s. All of these revolutions changed the way we think about science and society. All 4 of them have completely transformed science and society, and they will never go away. That goes for nano, that goes for every field of science, every field of engineering, every field of social and social sciences and economics. So this is a world-changing technology, just like molecular biology, cognitive, and the digital information age are. This is a picture of the National Nanotechnology Initiative budget for 2019, just as an example. The federal government in the United States has had a nanotechnology budget since the year 2000. It was put into place by Clinton, and then Bush signed it into law. And if you look at all the text on the right, which you can read later as you wish, let me just point out one thing here. If you go down to the 4th line at the top on the right, the budget for this year is $1.5 billion. And only a very small part of that would go into the earth sciences, but it does go into the earth sciences. It would be about 3% of that, actually. And that's still quite a bit of money. The environmental sciences would take up maybe 4 to 5% of that. So together, it's about 8 to 9% of the total federal budget. We are mostly funded through the National Science Foundation and Department of Energy and Environmental Protection Agency, all relevant to all fields of earth and environmental sciences. Okay, so that's the funding picture. I'm going to show you a cartoon next, so bear with me. You're going to see a big cat on the upper left. And the cat, a cat is a cat no matter how big or small they are. But if we make that big cat that same cat into a smaller cat, it's still a cat. And if we make that medium-sized cat into a really small cat, it's still a cat. It still does what cats do. But if you take that same small cat and change it to an even smaller cat, it becomes a dog. I saw this analogy made in National Geographic years ago, and I just couldn't resist. I think this is so symbolic of why nano has changed the world. You can take the same material, like a cat, and make it smaller and smaller and smaller. But when you make it so small that it's down in the nano range, it turns into a dog or something else. And once it's in the range of something different, as you change the size of the dog, it changes again and again and again, if you will, if you want to follow this analogy, to all the hundreds and hundreds of kinds of dogs that are out there. So let's look at this more specifically and get geologic here. Let's take the element gold, or the mineral gold. Let's call it the same thing. And when you take a macro-sized piece of gold, as you see in the upper left, and measure its melting temperature, it will melt at exactly 1,064 degrees. And you can do this experiment in your own lab in an undergraduate class, no problem. I mean, that piece that you see in the tweezers will look exactly like that, even at 1,063 degrees. But you get to one more degree and it becomes a puddle. And that's the melting point, and everybody knows that. But it's a good demonstration if you have the equipment. Now, if you just take a tiny sliver of that gold so you can barely see it, naturally you ask the kids and they go, yeah, okay, it's going to have exactly the same melting point. And then you get it so that you can only see it under a microscope, and it's a micron in size, not visible by the eye, but visible under an optical microscope. And put it in the oven, and again, it will still melt at exactly that temperature. But when you make it nano size, and I'm going to show you a nanocrystal and the melting point of a nanocrystal, it's dramatically different. So the crystal you see on the right, TEM image of a 5 nanometer gold particle, and you're actually seeing atoms there as silhouettes of atomic columns in the TEM image. And if you put that in the same oven and turn up the temperature, it'll melt at dramatically lower temperatures. It's still pure gold. It still has the same crystal structure. It still would be called gold as a mineral, but now its properties in terms of melting are completely different. And if you measured any other property of the gold, they would be also completely different. So should we still call that material gold? Oh, I guess you would, but it has completely different properties, which obviously is a non-starter when you ask anybody this question that's not familiar with nano properties. So this is a real head turner for even a freshman in college. Look at the color. Gold is gold in color. But if you make it really small, you can make gold whatever color you want, depending on its exact size. It can be pink, orange, red, violet, purple, as you can see in those vials. And that usually really gets the attention of just about anybody. When you're a chemist or a physicist or an engineer and you want your material to act differently, then you make it really small. And that will give it valuable properties. And that's why in today's market, every year, nano-enabled products, so these are products like your iPhone that are stuffed with nanomaterials in them to make them work. If you add up all the value of everything that's sold that has a nano-enabled function in that product, you get $1.5 to $2 trillion per year. So you can see how incredibly valuable these things are. We're calling this a purely science and technology revolution. All right. Let's go to one more function of gold. Everyone knows as gold as being inert. So you look in the upper left there and you see old money being dug up out of the seabed that's been there for hundreds of years, and it's still perfectly gold, because gold, everyone knows, is inert. On the other hand, in the lower right, when you make nano gold, as you see in the atomic force image on the left of 30 nanometer gold particles on a substrate, or on the right, that's a model of what those gold particles look like on the substrate. When you make them really, really small, down in the nano range, gold becomes highly catalytic. So that reaction that you see there, carbon monoxide plus oxygen goes to CO2. Gold is an excellent catalyst for making that reaction go at very, very high efficiencies. But if you try bulk gold, it doesn't work. It only works when it's nano in size. Okay. That's like taking, you all would recognize this obviously as the periodic table. And gold, I don't know if you can see my pointer, but gold is the third in the right of the transition metals in the third row down, that's element 79, that's gold. We are now looking at gold as being different. And so it's different depending on what size it is down in the nano range. So it's almost like taking the well-known periodic table that all freshmen know about and study, including in earth science. And it's like taking that periodic table and doing this to it, but just putting it on its side and just mapping out a bunch of periodic tables. And that happens in the earth. It happens with minerals. It happens with all earth materials, liquids, solids, gases. Anything on the earth, anything on the planet that's used for any kind of technology or science will change, even gases and liquids, when they are in very, very small confined spaces or just as very, very small entities. So when you show this to a student, it obviously becomes extremely earth and environmentally relevant. And so let me just say right here that every field of earth science, paleontology, sedimentology, petrology, space science, ocean science, any kind of fluid science, the atmospheric sciences, all have nano relevance all the way through every system. Okay, I haven't talked about scale yet, and this is a really good way to get people interested. You take and scale, that is, you take a soccer ball and you go to the right by increasing the soccer ball 8 orders of magnitude. So take the soccer ball, get it 10 times bigger, and then 10 times bigger, and then 10 times bigger, and you do that 8 times, and you get to the size of the Earth. If you go the other way, take the soccer ball, make it 10 times smaller, and then 10 times smaller, and 10 times smaller, and you do that 8 times, you get to the size of a single nanoparticle that's 1 nanometer in size. That's 10 angstroms. So it's really fun to think of a soccer ball as exactly between, in orders of dimensional scale anyway, exactly between a 1 nanometer particle and the Earth. And that really gets people thinking about how small nano is. Wonderful graphic. And let me show you that even though these things are small, just like the periodic table, they affect how the Earth works. They affect the whole Earth system. So as it says there at the top, so what's the big deal in the earth sciences? And here's an example. So you look at the northern hemisphere there at North America, and you see an overlay of these diamond-shaped crystals. And these are actually just hematite, iron oxide nanocrystals that are found throughout all soils, pretty much around the planet. When the soils weather and the soil particles get to the oceans, either by wind currents as dust or by rivers that lead to the ocean, of course, those nanomaterials, like hematite nanomaterials, get to the ocean. Normally as earth scientists, we wouldn't even notice these because these are so small. You need a very powerful electron microscope to even find them and see them, but they're there. So anyway, those iron oxide nanoparticles, hematite in this case, get into the oceans. And then what do they do there? Well, in the lower left, you see phytoplankton, which are, of course, photosynthesizing microorganisms that are on the surface of the oceans in great quantities. And there's so many there that, as you see in the lower right, that these phytoplankton create half of all photosynthesis on Earth. So, this is something that kids learned about in high school in terms of photosynthesis. And the key there is the part where you take CO2 and the photosynthesizer will break it down to carbon, which goes into organic carbon and give off oxygen. All right, so that's what these phytoplankton are doing. But anyway, how do these phytoplankton reach the vast populations they have in the oceans? The major micronutrient that phytoplankton need in the oceans is iron. Where does the iron come from? Because iron is effectively insoluble in ocean water. So there's horribly little iron dissolved in the oceans to be a micronutrient to vast quantities of phytoplankton. So where does the iron come from? Well, what biologists have learned in the last 10, 15 years is that most of phytoplankton are getting their iron from iron nanoparticles that came off the continents. So Anyway, the point is simple. You start with iron oxides as nanomaterials on continents. They get into the oceans. They're used as a necessary micronutrient by phytoplankton, which gets their populations up really high. They pull down a lot of CO2 from the oceans and therefore from the atmospheres, and they produce oxygen. The higher the population of phytoplankton, the more they'll be taking up CO2, including from the atmosphere. So it's actually cooling the planet. People have actually thought that maybe we should use excess nanomaterials that we purposely put in the oceans to get the phytoplankton populations high to bring the overheating Earth's temperature down. Nice idea. There's a lot of issues with doing that, actually, which we won't get into here. But anyway, it's a good example of how these seemingly inconsequential nanomaterials on continents actually help control, through this series that I just talked through, the temperature of the entire planet. So there you go. A really great application of having to understand nano to understand these kinds of processes. All right, this is I'm going to end here very quickly, just another 2 or 3 minutes. This is a map that shows the amount of nano that's traveling across at least the surface of the Earth. Look at the dust storms in the right of this picture. What that 320 means is that every year there are 320 teragrams of nanominerals in those dust storms that distribute themselves as where you see the arrows going. And a teragram is 1,000,000 metric tons. So what I'm saying in dust storms is that every year on this planet right now, 320 million metric tons of nanomaterials are in those dust storms that distribute through the planet on landing, on the continents, on the ocean margins, and in the open oceans. That's 95 on the right. So that would be 95 million tons of nanomaterials per year are landing in the open oceans. Many of those are iron oxides. All of those would be used by phytoplankton to get their populations where they are, and so on and so forth, as I told you in the last slide. In the middle of the slide, in the lower part, you can see rivers in white. So this means that 1,000 to 10,000 teragrams of nanomaterials are brought by the rivers every year to the continental shelves and deposited in the oceans there, and so on and so forth. So whatever your favorite system is, at least on the surface of the planet, hydrothermal vents in the lower right, glaciers and icebergs are melting and dropping nano into the oceans, things like that. You can just follow it around. And we also have incidental nanomaterials that are made by things that people do, and they're made unintentionally, but they're coming out smokestacks and fires, as you can see there, 1 to 10 teragrams per year that we have to think about. Engineers make 0.3 teragrams per year of engineered nanomaterials that end up in, as you can see there, in wastewater treatment plants and in landfills and all that kind of stuff. So that shows you how these things are distributed, at least on the surface of the Earth, and you can go into the interior of the Earth and do similar things. I'm not going to go through all this, obviously. I'm just going to show you that we all know, as Earth scientists, we have the water cycle and the rock cycle and that kind of thing. Well, nanomaterials have cycles too. And on the upper right, we have Earth components that contain nanomaterials. On the upper, sorry, that was the upper left. The upper right, we have the precursors of the materials, which are electrons and protons and elements and ions and polyatomic ions and stuff. Then as you go in the middle of the bottom, you get the nanomaterials. And the nanomaterials there on the left, that's a carbon soot, which are nano, which we breathe, and especially in cities that have a lot of carbon soot exhaust. The one in the middle there is the aqua color in purple. That's actually a virus. A virus is nano in size. It's a biological nanomaterial. We threw it in there just because we didn't want to put another mineral in there, but we could put any mineral in there you want. And then that's a carbon nanotube that's obviously engineered. And all these things are in the nanomaterial cycle of our planet. Okay, now all of this is summarized. Dave will talk a little bit more about this, but we just Dave and I and 13 other authors just published a paper in Science, which is 13 pages long. And it's called Natural, Incidental, and Engineered Nanomaterials and Their Impacts on the Earth System. Anybody that's interested in getting a really broad picture of nano in the Earth system, I would look at this paper first. It's really comprehensive, covers everything we possibly could in 13 pages in Science, and about 130 references that Dave will be talking about later. And I'll go on. I think I'm almost done here. Mitchell, can you get back on and tell me how many more minutes? I could stop here or I could go on for about 3 minutes, but I don't have to.
I think we could probably take some questions if anyone has them. They could enter them into the chat box. I think we have some time. So if you've got a few more slides, I would say go ahead and do those.
Mike, I'd encourage you to go finish your slides, please.
Okay. All right, I'll finish these. So I think there are 3 more. So just to give you a little bit more detail on this, in this picture in the upper left is an iron, well, that's supposed to be an iron atom in the middle that's coordinated to 6 water molecules. And so when iron is truly dissolved in ocean water or river water or lake water or groundwater, that's what it looks like. If you go down below that, you'll have 3 of those clusters that are put together, okay? Now, each of those clusters, if you were to put a solid form on it, would be an octahedron. And so when we put more clusters together, as we move to the right, you see all those octahedra that are stuck together. So that's, a couple hundred of octahedra stuck together. And that's, you can see the 1 nanometer scale bar in the lower right. That's now a 5 nanometer piece of hematite. And the one above it is a 1 nanometer piece of hematite. So all of these things are smaller than 5 nanometers, obviously. They go down to less than 1 nanometer in size. When you're filtering water, like river water, if you will, or groundwater, when you filter it, you usually put it through a 0.22 micron filter. That's standard by geochemists and hydro people. 0.22 microns is 220 nanometers. So all of these things easily go through those filters. And aqueous geochemist, and I'm one of them, would call all of this stuff dissolved. But as you can see, or you can guess chemically, they would all behave different chemically, whether it's truly dissolved like in the upper left, or the tricluster there below that, or the 1 or 5 nanometer particles would all behave differently. And in the nano world, we actually measure those properties, and I guarantee you all of these things behave chemically and mechanically and physically and electronically and gravitationally and everything. They all behave completely differently. So in the old days, we just said, oh, it goes through a 0.22 micron filter and it's all dissolved and we'll treat that all the same. The iron is dissolved. Well, what we find is the world is really way more complicated than that, and that's what this is meant to indicate. To actually look at stuff like this really close up, we can do electron tomography, which gives us a 3-dimensional look at how, in this case, these iron oxide particles look, the ones I was just graphically showing you. This is what they look like in 3 dimensions. And we would call that dissolved? I don't think so. But those would easily go through a 0.22 micron filter. And by the way, the green sort of tubes that go through those are actually nanotubes that go through these nanocrystals. And those nanotubes that are usually just filled with water, if they're in an aqueous system, behave very differently, and that water in there behaves very differently than bulk water. And I'll just end by flashing through the fact that if you really want to understand how these properties change so dramatically, you really do need to go to quantum mechanics. And to do that, it's actually not as bad as you think. I've taught freshmen enough quantum mechanics to understand why these properties change so dramatically. And just to give you an example, oh, there's my quantum skier that goes through both sides of the tree at the same time, because in the quantum world, you can do that. And it's fun to talk to young people about why that is and where all this kind of science came from and what it means, and at levels that they can understand at that age, which is really not a problem. And my last slide is this. I just want to, actually, I'm just going to go to this one. When you finish calculating all of these things, which is really not so horrible, the second line from the bottom, you see that for hematite, the quantum confinement in hematite, you do this calculation and the calculation gives you 10.8 nanometers. That means that for this quantum mechanical calculation, which I can actually show freshmen how to do, it says that when the mineral hematite gets below about 11 nanometers, it will start acting bizarrely. And it would look like the pictures I just showed you a couple slides ago, those tiny clusters of those iron octahedra. And the properties will completely change. And if you want to do it like for a sulfide, like galena on the bottom line, if a galena crystal gets below about 18 or 20 nanometers, it will start to behave completely differently. So if that galena is like in an ore deposit and it's like 15 nanometers in size, it's not going to act like normal galena anymore. It'll be completely different. And ore petrologists or geochemists love this kind of science because it helps them understand ore deposits, just as an example of application. So that's it. I'm going to give up my screen here. You should have control now, Mitchell.
Yeah, and actually Dave can take over the slide share. And while we wait, maybe we can take any questions if people want to enter them into the chat box.
There is one question, and that question is there any significance of particles at 10 nanometers or 100 nanometers, or only at 1 nanometer or less? Mike, you started to answer that in the last slide. And why don't you expound on that, and I'll load my slides.
Okay. So again, is there any significance of particles? Yes, there is significance in terms of these tiny particles, in terms of amount, and in terms of relevance. You know, it's interesting because you don't find things unless you look for them. And about 20 years ago, I just went off on this quest to try to find, you know, where nano is and what it is in the earth and in the environment. And everywhere I looked, I found it. I found nano things, and I found a lot of them. And so nano is everywhere. We're breathing it right now. A lot of it's naturally occurring that we're breathing right now. By the way, with every breath you're taking in, if you're in like a normal, you know, structure in North America and not in the middle of Mexico City or Beijing, China, you're probably breathing about 2,000 or 3,000 nanoparticles per breath. If you're in a bad day in Beijing, you're breathing 50 million nanoparticles per breath. A lot of those will be naturally occurring. A good number will be incidental, and some will even be engineered. If you go in any soil, you'll find vast quantities of these things. You just need the instrumentation to find them because they're so small, obviously. If you go in any lake or river or groundwater or ocean, they're just loaded with this stuff. And if you're in a rock, you will find them, especially at grain boundaries. Yeah, so they're everywhere. And they're doing stuff. And we've ignored them for all of these years. Good question, thank you.
Okay, well, this is Dave Moak from Montana, and I'll finish up this webinar with some thoughts on how we can teach about nanoscience across the Earth and environmental sciences curriculum. There we go. So it is indeed a brave new world in this nano world, and not many of us are trained in doing nanoscience research. And so, as usual, we convened a couple of workshops, and put together an extensive web resource for all of you to use, hopefully to help jumpstart your own interest in teaching and learning about nanoscience. So this is the top page of the module. And what we're trying to do is to link state-of-the-art science that Mike just talked about with instructional practices. So we follow the usual integrate and cutting edge format of what, why, and how. And so we try to provide some of the background information you need to understand what nanoscience is. And this really falls into three categories. The characterization of nanoparticles. Our friends in engineering are concerned with manufacturing nanoparticles. And then as earth scientists, I think, as Mike just said, the discovery of nanoparticles, natural nanoparticles, incidental and engineered in all parts of the Earth system. We provide some of the basics to get you started. We talk about nanoscale. Mike has already talked a little bit about this, different types of nanoparticles, relationship of surface areas to volumes. I'm a mineralogist and crystallographer, and so I'm interested in classical nucleation of nanoparticles and growth of nanoparticles. And then these whole families of size-dependent properties, and these could be physical properties, optical properties, solubility properties, and much more. On this introduction, we have links to numerous multimedia short video clips that are produced from a number of sources that, again, you can use yourself or with your classes. Why teach nanoscience? Well, there's a number of reasons. Mike made the case that we're really missing the boat if we don't teach about nanoparticles in our courses, from introductory all the way through upper division courses. We really owe it to our students to expose them to this exciting new field of research. In addition, the National Nanoscience Initiative has placed this as a high priority for research in the United States. Nanoscience is a major economic driver on the order of $3 trillion in nano-enabled materials by the year 2020, on the order of $10 billion a year of research funds from all sources, not just federal, but also industrial as well. We're really missing the boat if we don't prepare our students for the future workforce needs in nanoscience. And there's a whole range of societal issues that are addressed by nanoscience as well. And we'll come back to those in a few minutes. So the way I put it is whatever you think you know about materials on the meso or micro scale is probably wrong on the nanoscale. And Mike just made a good case for that. Again, the physical properties, mechanical properties, chemical reactivity and toxicity are all different when we deal with particles on the nanoscale. And one last thought, a big initiative at NSF is convergent science, and there's no better poster child for doing convergent science than nanoscience. Convergent science really requires deep integration across all disciplines. Nobody owns these issues of how nanomaterials operate. We need people from engineering, physical science, life science, earth and environmental science. And there are these really broad-ranging topics that we should be at the table and contributing to. Questions of environmental health and human health, energy storage and energy transfer, and much more. So we ignore nanoscience at our own peril. How do we study nanoparticles? Well, we have a whole arsenal of the whole alphabet soup here of analytical instruments that we use, transmission electron microscopy, Raman spectroscopy, and many others. But there's many, many things that we need to know about nanoparticles to fully characterize them. And a partial list is on the left. We need to know the size and shape of the particles because, again, many of the physical properties are size and shape dependent. We need to know about textures. We need to know about the bulk composition of materials. And we also need to know about the surface composition. It turns out that 1 or 2 atomic layers on the surfaces of materials quite often are quite distinct from the bulk composition of materials. We need to be able to do elemental mapping, depth profiling, to give us a chemical stratigraphy across interfaces. We need to know the chemical state, the redox potential of components, and certainly the underlying atomic structure. So we have a large number of instruments that we use, and many of these are common to what we are already doing in classes like petrology, mineralogy, geochemistry, crystallography, and so on. So we have already put together a series of primers on many of these techniques. We're always adding more, but this is a place where you can go to learn the fundamentals of, for example, X-ray powder diffraction, scanning electron microscopy, elemental analysis, and much more. All of these techniques have pages similar to this. This happens to be time of flight secondary ion mass spectrometry. But again, we try to present just the basics about what the instrument is, some of the fundamental principles, how the instrument works, typical applications, strengths and limitations, and then some examples of how we collect the data, present the data, and then supporting literature as well. So if you want to know how we study and characterize nanoparticles, please think about going to these instrument sheets. We also, on the website, have PowerPoints from experts that were presented at 2 Goldschmidt conferences in 2017 and 2018, and another workshop that Mike and I convened called Nano-Earth 2018. All of the PowerPoints can be downloaded from the program pages from each of these websites. And I'll show you a few slides in just a minute from some of these presentations. And the one thing that I think I'm most proud of in this project is, as a result of writing the science paper, I compiled a bibliography of over 500 references that were recommended by the experts in the field. And we've organized these into categories that will help support your own teaching in nanoscience in the earth and environmental sciences. And you can see a couple of the headings that we have here. Questions of where nanoparticles are in the Earth system, their fate and transport in the Earth system, again, characterization. Here's an example of some topical issues such as nanoparticles as airborne pollutants, and these could be natural particles, the pioneering work of Peter Busick and his colleagues looking at airborne nanoparticles, anthropogenic particles as a result of coal combustion and so on, and nanoparticles as they relate to climate change. So this particular collection of resources provides a large number of high quality vetted resources so that in your class, if you would like to do a short unit, maybe a lecture, maybe a problem set, maybe a discussion on the role of nanoparticles in a certain part of the Earth system, this is a place where you can go to get credentialed, easily accessible information. So how to teach nanoscience? Well, you all know the party line. We're into active learning whenever possible. Let's have the kids get their hands on the instruments. There are many opportunities to do nano research in our standard classes. The group on the bottom is a bunch of my mineralogy students doing X-ray diffraction on clay minerals. We also recommend teaching from the primary literature. And here are some recommendations from the Teaching Petrology workshop on strategies that you can use for using the primary literature in your own classes. And again, using the resources that we put together in the collection of references can easily be brought directly into your own classes. And then we also have previously formed special collections. This one is on teaching clay mineralogy. And we have had this online for some time, but you might recast this in thinking about clays as a special type of nanoparticle as well. It's extremely important in all aspects of the Earth and planetary system. So I want to give you just a few examples from across the Earth system of topics that you might want to explore in your own classes. And I guess I'm posing this as a series of questions about what's missing in what we're already teaching and how can nanoparticles fill that gap. And so one important consideration, Mike's already shown this slide, but in all of our concepts of global biogeochemical cycling, what's missing is the energy and mass component that is contributed by nanoparticles in the various parts of the Earth system. So whether it's rivers, glaciers, airborne, we simply are missing a large amount of mass in any models that we put together with respect to crustal and global cycling. I'm a mineralogist and a petrologist, and I'm very secure in my teaching of the Gibbs phase rule. But on the nanoscale, I think we also have to think about, well, what does a phase really mean and what's missing? Well, what's missing is a consideration of surface energies. And when we deal with the macro and micro scale, typically the surface energies are small compared to the overall Gibbs free energy of the system. But when we get to the nanoscale and surface energies become exceedingly large with respect to the volume of the material that we're looking at, those surface energies become very important, and they have to be considered in any discussion of phase equilibrium and how minerals nucleate, crystallize, and grow. The other thing is, excuse me, typically when we teach about crystallization processes, we look at what could be called classical nucleation and growth, where crystals grow one building block at a time, like bricks in a wall, each atom taking its place in a crystal structure. But increasingly, we're finding out that there are indeed non-classical pathways, and quite often these involve the early formation of nanoparticles of many types. These quite often are become ordered aggregates, and we get oriented attachment of nanomaterials that ultimately lead to crystallization. So just in our basic coverage of how crystals nucleate and grow, we're missing the boat if we don't also consider nanoparticles. And I'll just pass through those. There are also nanoparticles that are involved in many, many types of reactions that we don't spend necessarily a lot of time with. Catalysis, sorption, and the actual solution and precipitation reactions that occur right at the interfaces of minerals. Redox reactions and biomineralization of microbial EPSs, exopolymeric substance. Those are the polysaccharides that are excreted by microbes that can organize minerals. Here's an interesting example. This is green rust. It turns out that in many processes, nanoparticles form, but they're quite ephemeral. And unless you know to sample for them and to look for them, you will miss them completely, even though they are important steps in crystallization sequences. They may form early, react out, and if you only look at the products and reactants, you would have no idea what the actual reaction pathway is. And so this is looking at green rust. It has a very short residence life because it oxidizes almost instantaneously. And so you have to go to some fairly special sampling procedures to collect this and to be able to observe it. Nanoparticles in submarine hydrothermal systems. Well, they're involved with any number of reactions. There's pyrrhotite plus hydrogen sulfide to produce pyrite and liberating hydrogen. Well, hydrogen can be an important nutrient for microbial life. And again, if you don't know to look for the nanoparticles, you would completely miss these reactions. And in addition, nanoparticles can also be involved with abiotic reactions involving CO2 to produce simple hydrocarbons. What do we know about nanoparticles and some of the big questions? For example, the origins of life. Can clays possibly be a substrate for organizing or early stages of organic compounds? And many people, again, have surmised that it is black smokers that were actually the cradle of life on Earth. So what is the role of nanoparticles in those events? And in the history of Earth, what is the role of nanoparticles in the formation of banded iron formations in response to the great oxygenation event? Again, we don't look, we won't see it. And coming up to contemporary environmental issues, microplastics are all through the biosphere. And this is from Pete Weichseland's work. Nanoparticles are everywhere, and they're in huge abundances and are certainly affecting the biosphere. Nanoparticles in the atmosphere. Mike's already alluded to the great dust storms, but we also have salt sea spray. We've got volcanic eruptions. And then we have all the anthropogenic sources, whether it's diesel fuel, coal-fired power plants, and so on. These all infect not only natural systems, but human health as well. And nanoparticles play an important role in climate change. So if you're doing a unit on climate change, don't forget about the role of nanoparticles in the atmosphere and their ability to either absorb or reflect solar energy. Nanoparticles are in the groundwater that we drink, and this is near and dear to the Integrate project. There are many, many pathways to our drinking water. Some of it can be deposited by air, others can be brought via natural hydrologic systems. Large number of nanoparticles make it to the waterways via wastewater treatment plants. And in all these cases, we're finding metals, we're finding persistent pharmaceutical chemicals in the form of nanoparticles that affect our health as well. If you're doing a unit in environmental geology, on acid drainage, for example, or in economic geology, this is the Iberian Pyrite Belt. Very pretty, but also very toxic. And what's happening is that strange nanominerals, this one is schwertmanite. It's an iron oxyhydroxide sulfate, but it turns out that schwertmanite is probably the most important phase in terms of iron solubility in the system, and also as a sorbent for trace elements such as copper, zinc, and arsenic. Nanoparticles related to radioactive waste disposal. Head over to Hanford and take a look at what's going on there. This is Nick Kofakiu's work. And nanoparticles are involved with redox reactions. They're involved with sorption. And in this case, it turns out that pyrite in the form of these framboidal pyrite spheres that you're looking at here are involved with precipitation of uranium oxide as part of this redox reaction. Nanoparticles are in all kinds of things that we eat, and it's also in sunscreens. This stuff becomes bioavailable and can be transferred among the organs in the body. So if you're interested in in human health, in environmental geology, nanoparticles are an important point. And I want to close with a call out to Cynthia Hall at Westchester University. She's been doing class projects based on lead in her class, and she has her students mobilized to go out and sample sites around Philadelphia. They initially use a portable X-ray fluorescence spectrometer to look for lead. They subsequently have done SEM and EDS work and X-ray diffraction and so on. And they have put together historical maps. All of the symbols that you're seeing here are former sites of lead smelters in Philadelphia. And they put together a really nice GIS based on this work. So I just wanted to show you that today, it is indeed possible to introduce nanoscience into your classes in an in-class research-based project that your students will be able to make a real contribution, as we can see in Cynthia's work here. And then finally, I couldn't quit without saying a few words about ethics in nanotechnology. We do indeed have a large number of resources available with respect to ethics related to release and transport and fate of nanoparticles. And getting back to Mike's example of fertilizing the ocean with iron, this is indeed an ethical issue. Mike started to talk about this, but are you prepared to make the decision to fertilize the ocean and to accept the consequences? So we can indeed sequester CO2 and large amounts of it. But as we do that, we also eutrophy the ocean waters and create a big dead zone. So this is a great case study that would only take a few minutes to introduce into any number of classes, not only the science, but also the ethics that are related to this. So let me just close by saying this is an invitation to everybody. Please use these nanoscience resources in your own current coursework. If you develop a nanoscience teaching activity, please contribute to our teaching activity collection, contribute your course syllabus, and if you find other cool resources that you'd like to share with the community, you can put it in the contribute box. And for those of you who are willing and able, we're looking for a number of people to help us with the usability study for this website. So please send me a note afterwards if you would be willing to do a bit of a follow-on walkthrough of the website and help us understand what works and what doesn't. And with that, I'll hand it back to Mitch and take any questions. Thank you.
Yeah, we've got a minute or two for a question or two if there are any. So you can wait a second and see if any of those come into the chat. And actually, maybe while we wait, I can do my end of webinar spiel. So we have some upcoming opportunities for those interested. What will probably be the final webinar of the series for this semester is next week. Yeah, next week. Integrating energy, earth, and environmental education. As always, consider your department or course for NAGT's Traveling Workshops program. Our next deadline is June 15. Join us at the Earth Educators Rendezvous. That's happening in mid-July. Actually, and I think it's Wednesday, May 1st is our early bird registration deadline. So we certainly encourage you to register to get register by then to get reduced prices, and NAGT members also receive additional registration discounts. So consider becoming an NAGT member. We've got a webinar series discussion thread where you can continue the discussion from today's webinar, and I'll put a link to this in the chat. And as always, we appreciate your feedback. So if you have an extra couple of minutes today, it would be great if you wouldn't mind filling out our webinar evaluation and telling us what you thought about today's webinar. I'll also repeat Dave's call for contributing nano-related materials on their website. I've included a link in the chat box. And if you're willing to reach out to Dave about the usability study that they're running on the Nano website. I haven't seen any questions come into the chat, so get those in now if you want them answered. Otherwise, you can reach out either to Dave or in the discussion thread to ask those. And I'll end with a thank you to Dave and Mike for their great presentation today, and also a thank you to all of you who were able to join us this afternoon.